Okay, thank you very much for the invitation. Okay, so the title is Degenerate for Massey products over arbitrary field, and it's joint work with Alexander Mercuria. So first of all, let me start by giving some preliminary definitions, some preliminary notions. Massey products in Galois cohomology, it's group cohomology. Let's just say Galois cohomology. Okay. So, okay, let's just fix some notations for the rest of the talk. So gamma will be a profinite group. P a prime. And then I denote by C upper star gamma Z mod P, the continuous cochains, continuous gamma cochains. So this is a cochains, this is a VGA whose cohomology I denote by H star, gamma Z mod P, cohomology, and this is the usual profinite group cohomology of gamma. And then n will be an integer, at least 2. Okay, so I want to give the simplest possible definition in this context. I will not define what a Massey product is. I will only define what it means for a Massey product to be defined or to vanish. And then maybe later I will comment on how one can get the actual definition of a Massey product. So, but in order to do this, I introduce this group, UM plus 1. So it's the subgroup of unitriangular matrices. So say upper triangular inside of GLN plus 1 of FP. Okay, so this is a PCL subgroup of this of GLN plus 1 of FP. Well, not, it's a P subgroup. And we have a short exact sequence, a central short exact sequence, like this. So UM plus 1 is in the middle. We have ZP going to UM plus 1. Let's call this map iota. And the map iota sends the class of some number M to the matrix all ones and then M in the upper right corner. And then, okay, pi is defined as so UM plus 1 bar is defined as the quotient, pi is the projection map. You can think of elements of UM plus 1 bar as being matrices where you forget the upper right corner. So pi in some way forgets the entry 1 n plus 1 of the matrices. Okay, this is a central short exact sequence. In fact, this Z mod P is exactly the center of UM plus 1. And also we need another piece of this diagram. So we take Z mod P to the n. So here it's UM plus 1, but I take Z mod P to the n. There is a map here, rho, a homomorphism. Rho sends a matrix, unitriangular matrix, say A1, AN. So here A1, AN is the first upper diagonal, and then I don't know what is after that. But the image will be simply A1, AN. So the point is that if you have a upper triangular matrix, if you take some fixed coordinate, that will give you a function to Z mod P in general, not a group homomorphism. But if you choose the first upper diagonal, then these coordinate functions, they are actually homomorphisms. And so they define this map, this homomorphism rho. And this homomorphism rho factors through this, well, it's driven on the center, so it factors through pi. Okay, so we have this situation. Okay, and I use this equation to define what it means for a Massey product to be defined or to vanish. So what do we need? The input is a bunch of characters of gamma. So chi1, chi-n in h1 gamma z mod p. Okay, remember that this is just the continuous homomorphisms from gamma to z mod p. Okay, so we say that the Massey product, if you want, the n-fold Massey product, the n-fold Massey product chi1 chi-n, so is defined if I take the n tuple chi1 chi-n, so now this is each chi-I is a homomorphism from gamma to z mod p. So the whole thing is a homomorphism from gamma to z mod p to the n. If this homomorphism lifts to a homomorphism to un plus a bar. Okay, so I can lift along the vertical map in this diagram. Okay, this one here. Okay, and then if it vanishes if I can lift even more. So vanishes if the same thing. So chi1 chi-n lifts to this time un plus 1. So if it lifts along the rho. Okay, so if it lifts along the diagonal map in this time, this diagonal map rho. Okay. So let's just see the smallest possible example. So the case when n is equal to 2. Case n equals 2. Well, in this case, U3 is as small as it can be. So it's 3 by 3 matrices. We have ones in the diagonal, and then we have chi1 here, chi2 here, and so this is already everything except for the upper right corner. So we already have lifted to U3 bar, right? So if you want U3 bar, the map from U3 bar to Z mod P square is already an isomorphism. So chi1, chi2 is always defined. Because the lifting condition is always satisfied in this case. But when is it vanishing? Well, the diagram above simplifies a little bit. We can rewrite it as 1 ZP and then 3 and then ZP squared. And this is, of course, again, short exact and central. So we can take the group cohomology. So what do we have? We have H1 gamma U3, H1 gamma Z mod P squared. and H1 gamma, H2 gamma, Z mod P. So now here we have our chi1, chi2. We want to lift it to a homomorphism to gamma, from gamma to U3. So we would like to know if it comes from something here, right? Because H1 gamma U3 is just homomorphisms modulo conjugation. So we would like to see that this chi1, chi2 belongs, when it belongs to the image. Well, that's if and only if it goes to 0 here. But the image here is, one can do a computation, and this computation shows that the image here is the cup product, chi1, chi2. So yes, so chi1, chi2 is always defined, and it vanishes if and only if the cup product is 0. Okay. So this is the smallest possible case, but in general, we have at least the following implications. So in general, we have chi1, chi-n vanishes. So it lifts to un plus 1. If it lifts to un plus 1, then it lifts to un plus 1 bar. So certainly chi1, chi-n is at least defined. And then if it is defined, then at least all the no parentheses, all the cup products of consecutive chi-i's vanish. Basically by this n equals 2 case that I explained. So, but I want to add an extra picture here. So what does it mean? Just to remind one more time. So what does it mean to that the Massey product vanishes? It means, so here we have our chi-i's. We can put them in the first upper diagonal. And now we want to, so chi1, chi-n vanishes if we can fill all the other entries with this, so that the whole thing becomes a group homomorphism from gamma to un plus 1. And when is it defined? It's defined when we can fill maybe not the whole thing, but if we forget about this square, then we can fill the whole thing and make it into a group homomorphism from gamma to un plus 1 bar. And when do we have this condition on the cup products? We have it when we can fill, maybe we can't even fill un plus 1 bar, but we can at least fill the next upper diagonal. So, and then forget about the rest. So fill the second diagonal, second upper diagonal. And each of these entries, the entry between chi-n and chi-n plus 1 tells, between chi-I and chi-I plus 1 tells you that the cup product of the two is 0. It is a manifestation of the fact that the cup product is 0. Okay, so these are massive, and of course, so you could imagine, if you're trying to construct these homomorphisms, you could imagine trying to do it basically one diagonal at a time, and maybe in each diagonal one block at a time. And yeah, that becomes, as you can see, it becomes very complicated very quickly. Because as I said, only the first upper diagonal, they are really group homomorphisms. The rest are just functions which satisfy certain conditions. Okay, now so we're interested in the case of absolute Galois group. So suppose now the gamma is gamma f. So this is my notation for the absolute Galois group. Absolute Galois group of a field F. Okay, and just to simplify, so for simplicity here, let me assume that characteristic of F is not P, and that we have a T root of unity. Okay, so in this case, we can reinterpret this in this definition of Massey product being defined or vanishing in terms of elements of F, because the Kummer sequence tells us that H1F Z mod P is F star over P's powers, and H2 F Z mod P is the Brouwer group of F, P torsion. So what do we get? So so for all A1, AN in F star, we can what do we get? We get a Massey product. We can talk about the Massey product of A1 AN. We can say whether it's defined or it vanishes, because we just refer to the Massey product of the homomorphisms corresponding to A1 AN via Kummer theory. And we have the same implications. So again, we have that A1 AN vanishes. Well, if it vanishes, then it is defined. And if it is defined, the cup products are zero. Or what are the cup products here? They become, say, we're doing it with respect to the prime P. So we get the mod P cohomological symbols, A1, A2 up to AN minus 1 AN. This should be zero in the Brouwer group of F. Okay. That's, so in the case of fields, we can interpret everything just using the arithmetic of the field. Well, at least when we have a P field unit. And the, okay, now just very briefly, I want to say that there is, so I didn't define what a Massey product is, but there is, of course, a definition of what a Massey product is. So Massey defined these, the Massey products in algebraic topology in 58. And so maybe let's just say, so if A is a well, DGA, if A is a DGA over some FP, you can define the Massey products, say A1 AN is in the cohomology, first cohomology of A. Then you can define the Massey product of A1 AN. It's a subset of H2, and it is the definition becomes complicated. So it's still a reasonable definition for n equals 3, but then already for n equals 4, there are many conditions. So basically, you have to take the lifts of these AI, and they have to satisfy some recursive conditions, which become very cumbersome to write down. And you take all these liftings with these properties, and you use them to obtain elements in H2. And the collection of all these elements will be the Massey products, the Massey product of A1 AN. And then once you have this definition, you can say that A1 AN is defined if it is non-empty, because it could happen that there are too many conditions, and then you were not able to satisfy all of them. And then, but if you were able to, then it's the Massey product at least is defined. And then the Massey product vanishes if it contains 0. So the 0 element can be constructed in this complicated way. Okay, so this is basically this is the original definition due to Massey, perhaps refined by various authors. And then it was, so this is, I think the first time that they were used was 58, and then Dwyer in 75. Dwyer in 75 showed well, he came up with the definition that I gave above, and then he showed that let's call the Massey's definition reduces to, well, our definition. It's really the Dwyer's definition. If we take A to be the gamma cochains. Okay, and of course, the topological definition, instead, you have to take the singular cochain complex as a DGA. Okay, but this is, we don't need to go through this, we just, because all we care about is when the Massey product is defined or vanishes, and that has this simple interpretation in terms of these homomorphisms. Okay. Now, part two. Part two is the Massey vanishing conjecture. Okay, so what is the one of the most important problems? Extremely basic problem, but perhaps also impossible to really completely solve, is in this area is the profinite inverse Galois problem. Inverse Galois problem, which is also, which I phrase very vaguely as which profinite groups may be realized as absolute Galois groups of some field. So there are some restrictions. For example, so first of all, it's probably impossible to make a list or anything like this. So what we can hope for is to construct invariants or come up with restrictions, for example, restrictions of the cohomology, to try to pin them down as much as possible. And a spectacular development in this direction was the Blockato conjecture, that in particular says that if gamma is the absolute Galois group of a field F, then the cohomology has a very simple structure, has generators in degree 1, possibly many, of course, generators, but they're all in degree. You can choose them to be all in degree 1, and relations in degree 2, quadratic relations. Okay, so in some sense, the Massey vanishing conjecture tries to move forward this consequence of Blockato, so to better understand this H star gamma ZP. So what is this Massey vanishing? So Massey vanishing conjecture. So this was formulated by Minach and Tan. The paper appeared on the IFREM in 2013. And this is their conjecture for all fields F, for all N, at least 3, for all P, primes P, if an n-fold, so if a Massey product, n-fold, Massey product is defined, then it vanishes. So this is the conjecture. It tries to go beyond Blockato because there may be profinite groups whose cohomology has generators in degree 1 and in degree 2, but which is still, they're not profinite, they're not absolute Galois groups. And so the one way to show that these are not Galois groups would then be to show that there's some Massey product that does not vanish, that is defined but does not vanish. So this is another, if this statement is true, it would say that in a new way, the cohomology of an absolute Galois group is easy, right? it has simple generators and relations, and also all these higher massive products, so these higher product operations, they vanish. They're trivial in this case. Okay, so let me just, I don't want to make the whole history, which is there are many papers on this topic, but I want to say that the main case is when this conjecture is known, n equals 3. So the first work was Hopkins Wikelgren, which is the fundamental work in this area, because they began attacking this massive vanishing conjecture before it was even formulated. So they are the ones that started this whole thing, and they proved it when n is 3 and p equals 2 in the case of number fields. And then subsequently, Minach and Tan, and then Efrat Massey, I think essentially simultaneously, they did the case. They did the rest. So they did the case when still n is 3, but the field and the prime are arbitrary. There's a number of works. Okay, and then the other important result is the case when f is a number field. And this is due to Arpaz-Wittenberg. I didn't write down. I think probably it was published maybe last year or this year, and posted a couple years earlier. And F number field. So the field is small, but then any n and any p. So very strong statement. And so what is the main difference between what is that makes number fields easier in some ways? That we have more techniques available. In particular, we can try to use local global principles. So the case of local fields for this conjecture is known, is very easy, very explicit and very easy. And so one can try to patch together the solutions coming from local fields to obtain solutions over global fields. So this is, of course, easier said than done. There is a lot of work involved, but that is the main line. And this line of attack was already suggested by Hopkins and Wikelgren, who did it in the special case of n equals 3 and p equals 2. And it was carried out fully. So there is a lot of work. It was carried out fully by Arpaz and Wittenberg in the work. Yeah, it's a long work with many ideas and strong. So a stronger version of this conjecture. It's not a conjecture, it's just a property, because it can fail. So let's just call strong vanishing or strong Massey property for a field F. For a field F, let's suppose that F contains a p-fruit of unity. Then again, this is due to Minach and Tan. They phrase it as a question. Minach and Tan. So this is the following stronger question. So for all n and for all p, I don't ask that if the Massey product is defined and it vanishes. I ask that if the cup products vanish, then the Massey product is vanishing. Okay, so stronger property. And as I said, this is false because of this. There is an example due to Arpaz and Wittenberg. It predates their work on the number field case. So F is equal to Q. If I take the prime P equals 2, and I take, well, I consider these cup products, so 34, 2. So they're two. two cohomological symbols, then 217, and then 1734. So these are all zero in the bar group Q, but if you consider this Massey product, 34, 2, 17, and then 34, this is not defined. Okay, so it's also non-vanishing. It's not defined and therefore not vanishing. So it's not enough to say to require basically if you want to fill to the whole UN+1, it's not enough to assume a lifting to the second upper diagonal. You really need to assume all the diagonals except for the last entry. So that's a conjecture, of course. But if you only assume the first one, then it's not enough, as this example shows. Okay, but still, this is an interesting property to look at, to consider. And then there is an even stronger property, which is the formality property. And this was already considered by Hopkins and Wickelgren. So the formality property, again, for the field, is that the DGA, this DGA, say gamma F, sometimes I will just write F, is formal. So the DGA of cochains is formal, meaning that is it is quasi-isomorphic to its cohomology algebra with zero differential, with differential equal to zero. So if a DGA is formal, then in this sense it's quasi-isomorphic to the cohomology algebra with the differential equal to zero. Then all Massey products for any at least three, they're all automatically defined and they all vanish. Very simple observation. So, but it gives us the following chain of implications. So formality implies strong Massey, and it implies a strong Massey implies Massey. And we are not allowed to go back here because of F equals Q, our Wittenberg. And we're not allowed to go back here also. This is due to Positselsky 2015, I think. So, and the counterexample is some, so I have some local fields. It proves it for some local fields that they have this local fields. They always have the strong Massey property, but some local fields they don't have this formality property. And this is, as I said, is due to Positselsky 2015. Okay. So then Positselsky does a lot more in his paper, and regarding this topic of formality, and he poses the following question: Do there exist a prime P and a field F of characteristic different from P, such that F contains all roots of unity, or if you want, all P primary roots of unity. But still, the cochains DGA is not formal. Okay, this is because his argument used crucially that that not all roots of unity are in a local field, So that was an important part of his argument. But then he posed the question and he suggested that the answer should be yes, but he didn't have any examples. Okay, so this is the situation. We have these three properties: formality, strong Massey, and Massey. One stronger than the other. We know that Massey is still open, and the other two, they're false, and they're just properties. They're not conjectures. Oops. Okay, and then this is where my work with Alexander Mercurio fits in. We have some new results on these properties and on the Massey vanishing conjecture. So let me state my results, our results, new results. Everything is joined with Mercurio. So for now on, we assume that P is equal to 2. The prime P is equal to 2. Okay, so let me start from theorem 1. So theorem 1 is that the following. So for every, if you pick any field, any starting field f0, let's say a characteristic f0 different from 2, then there exists some bigger field f and some a, b, c, and d in f, no 0, such that the Massey, the cup products are all 0. The consecutive cup products are 0. But A, B, C, D, the fourfold Massey product A, B, C, D is not defined, and so it also does not vanish. So okay, and then as a comment, we can even take A equals D. So this will be a degenerate Massey product when the first is equal to the last element. And so in particular, this gives, if you take F0 to be a field, an algebraically closed field, for example, complex numbers, then you obtain a counterexample to, well, an example to Pozycelsky's question containing this field F0. And so if you take, as I said, F0 to be the complex numbers, then that answers Pozycelsky's question. You can take any algebraic closed field. And so also this gives, so this answers Pozycelsky's question. It also gives many new examples of this failure of strong Massey. Before we only knew about rational numbers. Now we have all these counterexamples. We can take them as large as we want. Okay, so that's theorem 1. Then theorem 2. Oh, and of course I should write the second one is we attack the smallest open case of the Massey vanishing conjecture. What is the smallest case? It's again the case n equals 3 is done, so the case n equals 4 is the next one, and we do the case p equals 2. So for every f different from 2, let's say A, B, C in F star, we can prove that if A, B, C, A is defined, then it vanishes. Defined, then it vanishes. So we cannot fully prove, of course, the case of if we could put a D instead of A in the fourth slot, then we would have proven the Massey vanishing conjecture for n equals 4 and p equals 2 over an arbitrary field. We cannot do it. We can only do it for this degenerate Massey product. Okay, this is okay. Yeah, let me just say one more thing. And then when the Massey product is even more degenerate, so theorem 3. Then So even more degenerate, meaning F, again, characteristic node 2, and we just take BC in F star, and we assume that A is equal to BC, basically. So BC, BC, BC. If this is, well, this is defined. Okay, let me say like this. So the following are equivalent. This is defined. This is vanishing. This is already a consequence of theorem 2. But then we add one more point, which is that -1 is in the image of the norm map from FBC star to F star. So here FBC star is when I put some scalars in the as an index, I just mean that I'm adding variables, and then I'm adding square roots, basically. So most of the time, this will be a B quadratic field extension of F. But then if B is equal to C, it will actually be only an étal algebra. Okay, it always has degree 4 over F. Okay, so we can say exactly when this Massey product BC, BC, BC is defined. It's the same as when it vanishes, and there is this explicit, relatively explicit conditions.
Maybe you don't need the star there.
Oh, sorry. Yes, thanks. Yeah, thank you. Yeah. And in particular, using theorem 3, so since -1 does not belong to the image of the norm map from Q 217. Okay, maybe for Q, let's just use the square root. Since this is actually a field, let's just use square root of 2, square root of 17 to Q star. This recovers our paths Wittenberg example. The previous example of our paths and Wittenberg, it's recovered by using theorem 3 and then computing that -1 is not in the image of this norm. This is still a non-trivial calculation. It requires some work, but I think that it gives at least an alternative conceptual explanation of that example, which is valid for arbitrary fields. Okay, so these are the results. Now, I would like to spend some time sketching the proof. Let's maybe start by sketching the proof of theorem 2. So what is this? Section 4. Section 4. So theorem 2 is the theorem if ABCA is defined, then it vanishes. So let's take, what do we have to do? We have to take A, B, C, D in F star, and we take them so that the cup products vanish. So of course, this is at the prime p equals 2, so there's 0 in the bar group of F. Now, using, for example, from the fact that AB is equal to 0, then just a standard reformulation of this fact is that there exists some alpha in FA star such that the norm of alpha is equal to B. And similarly, because CD is 0, there is a delta in FD star such that the norm of delta is C. Okay.
Oh, sorry. By the way, I mean, in the previous theorem, did you have to assume that the cup product of B and C is 0? I mean, sorry.
It's so no, I think it's correct as stated. So in particular, if any of these is true, then
I see. Okay.
all the cup products are 0. Yeah, yeah.
Got it.
Which then
Thanks.
amounts to saying that BC is 0, and then B -1 and C -1 are 0. Yeah, yeah, it's a consequence. Okay, now Guillaume, Minach, and Topats. They gave a condition for when a fourfold Massey product vanishes. So they showed that ABCD. Notice that I started with any D for now. ABCD vanishes if and only if there exists X and Y in F star such that alpha X delta Y, this Brouwer class, is 0 in the Brouwer group, the only one where it makes sense, which is FAD. Okay, so they prove this this condition, and then our idea was to try to find a condition for when the Massey product is defined, and then hopefully the two conditions will be equivalent to each other. That will, once you have two explicit conditions, ideally then you should be able to see that they're equivalent to each other. That was our original intention. So what we show that, well, given ABCD, we construct some E. So E is a scalar, but it's really, the construction is only well defined up to some subgroup. So the subgroup of this following subgroup, NA, NAC, and D and BD. So what does it mean? For example, NA is the image of the norm from FA to FA star to F, and similarly everybody else. Okay, so this E is a well-defined coset, and we show that. Well, I want to say something about the construction, but first let me say that ABCD is defined if and only if E is equal to 1 in the quotient. So it's equal to this. Well, let's just say 1 mod this. Okay. If it's a product of these 4 norms. Now, how do we construct this obstruction? Well, this obstruction to being defined. So let's go back to, let's go back to the matrices. So we have n equals 4, so n plus 1 is 5. That means we have 5 ones in the diagonal. And then we have, here we have A, B, C, and D. Okay, the first upper diagonal is, okay, it's the homomorphisms corresponding to them. And now we can do this. So you can think of this U5 as, so U5 as these two natural subgroups here. There is a U4 plus, which is this upper 4x4, and U4 minus, which is a lower 4x4. And these two groups, they're not disjoint, they intersect in a common U3, which is above the BC, right? This entry that they have in common. And the outer entry, we don't care because we're just trying to do we're just trying to show defined. So basically, if you want to construct a homomorphism if you want to construct a homomorphism from gamma to U5 bar, it's the same thing as constructing a homomorphism from to U4 plus, a homomorphism to U4 minus, and then they should which agree on the U3, on the middle U3. This is the idea. So now, how does the E come in? Basically, you pick a solution to the, well, we know, right, that the conjecture is true for n equals 4. So there will be solutions for U4 plus and U4 minus. So we just pick some solutions. We actually parameterize all the solutions without using the conjecture. In some way, we reprove the conjecture for n is. Yeah, we reprove the conjecture for n equals 3. So we parameterize all the solutions for U4 plus, all the solutions for U4 minus, and then we look at the difference the difference between a given U plus solution and a U minus solution in the intersection, and the difference turns out to be this E, this constant E, this scalar E. And we have agreement. This agreement is if and only if E is equal to 1 in that quotient. Okay, so we don't actually phrase. So I phrased it in terms of homomorphisms. We actually phrase this in terms of Galois algebras. So really, a homomorphism from gamma to U5 bar is a U5 bar Galois algebra. And that's the same as giving a U4 plus Galois algebra, U4 minus Galois algebra, and an isomorphism of U3 algebras in the corresponding to the intersection. And if you write down these conditions, it takes a work, but if you write down these conditions, you eventually get to this E that I mentioned. And so that's how we do this first part. So now we have our condition, and notice, so we have a condition for vanishing that's given by Guillaume, Minaj, and Topaz. We have a condition for defined. So they're both algebraic conditions. So one would like to see that they are equivalent, but we can only do it when A is equal to D. Okay, so we would like to show that the G and T condition is equivalent to our condition. And if you can do this, then you prove Massey vanishing for n equals 4 and p equals 2. But we can only do it for, for A equals D. Now in this, when A is equal to D, okay, let's see. Well, and what is the product of 4 norms really become a product of 3 norms. Right, this is the relevant product of 4 norms. This is the same as NA, NAC. Now ND is again NA, so I don't need to write it down, and then BD becomes AB. Okay, so maybe let's write it as AB, AC. Okay. And then, so to continue, we can also assume that F is infinite, because if F is finite, the conjecture is known. And then basically the point, once we have this condition, this reformulation using E, we put down coordinates, and we do some calculations. So let me start by saying what kind of coordinates. So so we can assume since BC is equal to 0, that means the conic corresponding to BC, the conic BX squared plus CY squared equals 1. It has some solution. So if you replace B and C by squares, you can assume that their sum is 1. And then we also have some for the other, we can only do this for B and C. We can also assume that a plus b is 1, but we can certainly find some v1 and v2 like this, and we can find some u1 and u2 like this. Okay, and we can suppose that the v1, v2, u1, u2, they are general, you know, because F is infinite. Okay, and then using this, we can define some scalars, R, S, and T. I will just to show that they're not that complicated, I will just write down one. The precise form doesn't matter, just to show that it's just some simple expression. For example, R is this, 2 v1 plus v2, u1 plus u2, and then v2, u2. S and T are similar expressions. Well, okay, I might as well write 2 v1 plus u1, u1 plus u2, and 2 v1 plus u1, v1 plus v2. And if the v1, the vi's and the ui's are generic enough, all of these are non-zero scalars. Just assume that every factor is non-zero. Okay, and now here's the structure of the rest of the argument. So we start from A, B, C, A defined. Then, well, we want to finish with A, B, C, D, A, B, C, A vanishing. And what we show is that they're equivalent by putting together all of these equivalences. ABCD is defined if and only if R is in this product, is the product of these norms, A, AB, AC. If and only if S is the product of these norms, and B, and AB, and BC. If and only if T is the product of these norms, and C, and AC, and BC. Okay, so now just very briefly, so this, the way these three numbers are defined, they satisfy this interesting relation, very symmetrical relation, that AR plus BS plus CT, they are 0 in the Brouwer group. So from the fact that they're 0, this is first of all, the fact that they're 0 is just a computation, and then it's a nice computation. Once you figure out the correct definition of these, it's not difficult, and then these equivalences that I'm pointing to with these two arrows, they follow basically formally from this identity. Okay, so the fact that R is in these norms, if and only if S is, if and only if T is a formal consequence of this nice identity. Now, how do we prove the first vertical equivalence? This is shown by basically, this is the way R is constructed. R is a if you use these coordinates, E becomes R. Right? Under these coordinates, E becomes equal to R in the appropriate quotient group. And yeah, okay. And how do we do this? Well, this is the hard part. This is the hard part. Just want to say that, so here, basically, so just one line, ABC A is vanishing. We have to use the GMT condition. We know that, what is it? There is X and Y such that alpha X delta Y is 0 over FAD. But now since A is equal to D, because A is equal to D, this FAD is actually isomorphic to FA squared. And so this condition is replaced by the two conditions alpha X delta bar delta Y equals alpha X delta bar Y equals 0. Okay, and now over FA. So two conditions over FA. And then, well, if you want to, you can sum them, and then you get alpha X. Since the norm of delta is equal to C, you can sum these two and get alpha C equals 0 and alpha x delta y equals 0 over fa. And then you have to work on each of these separately. And yeah, so then here there is still a lot of work, and in particular we at some point we have to use the theory of Albert forms attached to biquaternion algebras to basically solve this system of two equations. And what it turns out to be after a lot of work is that you end up with, you just magically this condition appears that T is in NC, NAC, and BC. Yeah, basically, okay, maybe I can just add one extra step. Sorry for right time. I can just say that, so here, basically, all you need is that there is an X such that X belongs to NC and BC. That corresponds to this equation. And then T and C and AC. And this would just correspond to this equation. And that is the same as saying the existence of such X is the same as this other condition here. Okay, so we moved from vanishing to that condition, and it is in to that condition, and it is here. It is here that we need this the material about Albert forms attached to biquadratic quaternion algebras. Other than that, the arguments they basically all rely in increasingly sophisticated uses of Hilbert 90 over Hilbert 90. Yes, and then for Positselsky's question, basically we some of the same material is used to answer Positselsky's question. In particular are the first part, our condition that ABCD is defined if and only if this E. We use this to construct the counterexample. Okay, yeah, sorry, I'm 3 minutes out of time. Thank you very much for your attention.
Thank you. Are there any questions?
So this last part, if you have a number field, everything simplifies extremely.
So I think no, I don't think there is an easier way to. I don't think our argument simplifies. No, I think because well, at least I don't know of a way to simplify our argument. Yeah, because the other argument is completely different using local global principles, and here we just do this. We just do algebraic manipulation.
Yeah,
so
I understand.
Yeah.
Any other questions?
Yes. What about odd primes?
Okay. What about odd primes? What we can do, we can do the first part. So okay, what about odd primes? So already, so let's say the case n equals 4, and then p is arbitrary. This we lose. There's no nice algebraic condition which is known for a fourfold massive product to vanish when p is odd. There is a sufficient condition. It's a sequel to the paper, but it's a sufficient condition which is probably very, very strong, much stronger than so far from equivalent. However, for us, we can give we have, so you cannot write this E in terms of in this F star modulo norms, but there is an alternative way that you can present this result, and then our result is true. So our condition holds for any prime, even odd primes. The problem is that then it's F, instead of being F star modulo some norms, it's F star modulo the image so the modulo the f points of some torus, say T of f, and this torus is not rational. It's very high dimensional and not rational. It's only rational when P is equal to 2, which is why we can parameterize everything. When P is odd, we cannot parameterize. We still have a condition we cannot parameterize, so we're not so sure what we can do with it. Yeah.
Thank you.
Any other questions? So your example in Theorem 1, the field F, is that
Yeah.
is that the generic construction? Is that the function field of some
it's
variety over F0?
It's basically the function field of a conic, but it's a little bit more complicated. So basically, you start from your F0, then you take F0 of say AB now are two variables over F0, and then you take the function field. So this is function field of affine space you want, and then you take the conic corresponding to AB, the function field of the conic corresponding to AB. So this is, for now, we are talking about the function field of a generic conic, and then take the two closure. This is E. This is so the two closure. So that's of course the fixed field of a two-zero subgroup. This is a field E, which has a number of so then okay, what are A, B, and C? So A would be that, B is that, and then C we define to be 1 minus B. And then what we have to do is to consider over E, consider X over E, the conic of equation corresponding to the symbol AC, AB, sorry. Okay.
No, you just killed that.
No, sorry, AC, I just killed it. Yes. I switched the ending. Yeah, so AC, the conic corresponding to AC. Okay, and now over sorry, and then F should be the function field. F is E of X. Now over this, we have AB is BC and then CD, which is CA here. This is 0. But then the Massey product is not defined. Not defined. And this uses the E construction. Really the fact that E is equal to R and then some residue computations. Basically, yeah, basically, if the number R, well, R now is a rational function on X. So if R was a norm from this, then the divisor of R would be the divisor of some NA plus the divisor of some NAB plus the divisor of some NAC. And then one uses elementary elementary arguments looking at the parity of the coefficients to show that this is not possible. So here we use the explicit form of that number R that I wrote above. Yeah, so this is the example F.
Thank you. Any other questions? Okay, let's thank the speaker again.
Thank you.